Welcome to part 3 of our lecture video series for Friday, May 5th, where we talk about gas stoichiometry. So let's remind ourselves about kind of generally the process for what goes down when we do stoichiometry. So recall, stoichiometry uses mole ratios and mole quantities. Specifically, it uses mole ratios to convert mole quantities of reactant into product or vice versa. Meaning that we need to have mole ratios, and those mole ratios come from our balanced chemical equation. So these are our reaction coefficients. And then we also have our mole quantities, and this is what we actually react. So let's remind ourselves about how we can get mole quantities typically. So if we have some solid that has a mass, we can get to moles of that solid by dividing by the molar mass. In all of our aqueous reactions, if we had a solution that had a volume, then we would multiply by the molarity to get our mole quantity of solutes. So now when we are talking about gases, I need to know something like a pressure, a temperature, a volume, and R, because the ideal gas law allows me to relate those variables in order to get moles N. In other words, N is equal to RT over PV. So this will give us a mole quantity of a gas. So the main idea is now we have another tool in our toolbox to use in order to get mole quantities of gases and relate those mole quantities to one another using mole ratios for a balanced chemical equation. So let's do one quick little example. So let's say that we've got 4.000 grams of H2O2 that is placed in a sealed 250 milliliter container at 500 Kelvin. What is the pressure of oxygen gas produced in atmospheres if we know that for every 2 moles of H2O2 decomposed, then we create 2 moles of H2O gas and 1 mole of oxygen gas. All right. So if I'm going to try to figure out how I can get the quantity of product, I'm going to first recognize that for every 2 moles of H2O reacted, that creates 1 mole of O2. So this is my mole ratio. And now I need to get my mole quantity of H2O2 reacted so that I can convert that using this mole ratio into some amount of oxygen. So let's remind ourselves of some of the conditions that we were given about the gaseous hydrogen peroxide reactant. So let's see here. We had this is not gas, this is solid. We had 4.000 grams. Okay. Now, since this is a solid, the way that I would get the mole quantity of solid is by dividing by my molar mass. So I know that 1 mole of H2O2 solid creates, okay, I guess the point is I don't know what phase this is, but it doesn't matter. I know it's mass. I know it's mass, so I can use molar mass. Let's see here. 1 mole of this weighs, looking this up, 34.016 grams. So let's do that division. So 4 divided by 34.016. This gives me 0.11759 moles H2O2. All right. So now I can use that mole ratio to convert my 0.117559 moles of H2O2 into some mole quantity of oxygen. So I know that for every 2 moles of H2O2 reacted, I generate 1 mole of oxygen. So I need to take my mole quantity of peroxide and cut it in half. This gives me 0.058795 moles of O2. And let's remind ourselves about what we're looking for. We are looking for the pressure. So since we want the pressure, I'm going to use the ideal gas law. So let's rearrange this to solve for pressure. So P is equal to nRT over V. I have my moles. I know R, that's a constant. Looking through my problem, do I have my temperature? Yes, I do. So I know my temperature and it's already in Kelvin. Lucky me. And then I have a volume, however, it's not in liters, so I do need to ultimately convert it. But these are things that we can do without stressing out too much. So the pressure of oxygen in the flask, assuming that all of that H2O2 had decomposed, is our moles, 0.0587 moles. Okay, times our gas law constant. Times our temperature, already in Kelvin, over our volume. So that was 250 milliliters, moving my decimal place 3 zeros over to the left. 0.250 liters. All right, so let's take our mole quantity, multiply it by our gas constant, 0.08206, multiply that by our temperature, 500 Kelvin, divide that by our volume, 0.250 liters. The pressure of oxygen gas that we get is 9.64957 atmospheres. All right, let's see here. Let's assume that these are all technically 3 sig figs instead of just the 1. So to 3 sig figs, this becomes 9.65 atmospheres of oxygen. So again, it's just a question of how do we get mole quantities and how do we convert mole quantities into pressures, and the means we have of doing that is the ideal gas law. Okay, I just realized that I have an appointment at 11, so I'm going to have to cut today's lecture a little bit short. So we will continue our conversation about gases, specifically looking at vapor pressure and the Clausius-Clapeyron equation coming up on Monday. So let's save for Monday, May 8th. All right, thanks guys. See you later.